Hello, everyone. Our next talk will be about recycling via code execution. Please welcome Aleks.
Hello, everybody, and welcome to my talk. Let's get it started. So who am I and why am I doing this? I used to live here in Novi Sad. When we started BalCCon about 10 years ago, I was here on the first conference. I was living here, but I have since moved, and I haven't been to BalCCon in many years, and I'm very glad to be back to finally be able to speak here again. I myself am a security researcher, and I spend my days reverse engineering software, finding vulnerabilities, and so on. But I thought it would be kind of an interesting idea to me to be able to use these reverse engineering skills for something fun, to apply them to some fun devices that are not highly impactful or high in value. And I wanted to talk about some of my existing projects, some of my recent projects, some things that I've published recently, to kind of introduce some ideas. So what am I going to be talking about today, and what's with the talk title and so on? My goal is to present my thought process when starting these sorts of projects, what my motivations are, what some previous inspirations for these sorts of projects were, and I also want to expand on some personal guidelines that I have when working on these sort of projects, and walk through a couple of examples as well with some steps, and hopefully in the end conclude with some takeaways, some notes that you can kind of apply further. So what is it with the title? Recycling via code execution. What do I mean by that? What I have in mind with that is repurposing existing devices by existing, possibly obsolete devices. By getting code execution on them, you can customize them, make them do things the way you want them to, and make use of the existing tools. Like Raspberry Pis and Arduinos are very available today. It's easily accessible, but with existing devices, you can get the benefit of somebody doing the hard work of industrial design. You can get a device that already has a nice case, battery management stuff, buttons, displays, maybe some special features, special hardware, special sensors. Additional benefit could be that the devices are much cheaper than it would be for you to make them, because it benefits from the economy of scale. And again, it's all for fun. I have here no hard targets. I'm specifically talking about weird, not super secure devices in this case. I'm interested in kind of something that's obsolete to breathe some new life into it. And this thing on the photo is, it's called Smart Response XE, which was a exam taking tool. I guess it looks like a calculator, but it's not. You can answer questions on it on an exam and stuff like that. But somebody figured out that it's pretty much Arduino compatible. You can flash your own firmware on it and make it do something interesting. So I took it and made it into a spectrum analyzer. There's an antenna on the back, and you can kind of repurpose the whole device, use the existing keyboard, use the existing display, and make it do something fun. So here's a couple of projects that serve kind of as inspiration, that embody the same ideas that I kind of wanted to present on. One is Travis's Good Watch, where he took a Casio calculator watch, figured out the board on it, figured out the layout, the dimensions for the connectors, for the display and the keyboard, and made his own board with the modern microcontroller that's programmable, so you can make a custom Casio watch with the custom firmware. This one actually had a radio in it, so you can make it send radio signals and have some fun. You would never be able to make a hobby project where you would be able to make it fit into such a small form factor with a nice keyboard and, well, quote unquote, nice keyboard and a display. It would always be more bulky than this, but again, benefiting from the industrial design of of the existing device, just replacing the guts with something that's more usable is kind of super fun. The other thing called ink plates, these are neighbors from Croatia, Radionica, who did recycling in a literal sense. These are recycled Kindle e-ink displays. E-ink displays are very expensive. They figured out a way to source a bunch of them, made a development platform for them that's easily accessible and programmable, and they're selling it and kind of doing the recycling as well. The weird looking device on the bottom is a project called Airbrake, initiated by Trammell Hudson. It's a CPAP machine, and if you remember in the early days of the pandemic, oxygen ventilators weren't all that available, there was a shortage of it. A CPAP machine can be turned into a ventilator machine with just replacing the firmware basically. So this project was recycling CPAP machines to do something else because the hard work of human-machine interface was already done. It's an already existing medical device. And yeah. So that brings me to a couple of my projects and the things that I wanted to talk about. One is this boxy device that came from my car. It's a infotainment system in a car that I wanted to get access to and have some fun with. And the other one is a very unusual camera. It's called Lytro. It's a very bad camera, but I wanted to have some fun to make it a little bit better. So coming to my first project about the Nissan head unit. So the story is, I got the car. It has this built-in infotainment system built into the dashboard. It's pretty nice, but it's very old. It doesn't have any new, it's like the navigation system it has is outdated. It has satellite radio, Bluetooth navigation, but it's all not really up to date, I guess. I could easily replace it with the aftermarket thing, like I could buy a different head unit and put it in place, but I wanted to kind of mess with this, try to get it to do something fun, and because it fits nicely in the car. It already has all the controls, it integrates, and yeah. So instead of replacing it, I decided to see if I can get access to it so I can change software, write my own extensions, or whatever. So why do I want to get, the goal with this project was to get root on the device so I can get code execution, so I can write my own programs for it, develop extensions and so on. Why? I kind of wanted to make it do something fun. It was obvious from the beginning that the thing runs Linux. So I figured if I get access to it, it's like any other Linux box, we can make it run additional programs and so on. And yeah, I was just curious about how it works. Whenever I'm setting out to start this sort of project, I find it useful to set up some constraints on the project and some end goals. Like, what am I trying to achieve if I'm reverse engineering a device? And what constraints do I have? I don't want to make it too complicated. I want to set some limit to what I am willing to, how far I'm willing to go with this project to kind of get access to it. Because if you put in enough time, you can get code execution on any device, but it doesn't make sense to spend too much effort and too much resources in a not so important device. So in this case, my constraints are no disassembling of the dashboard. So I do not want to break anything in the car. I do not want to take the machine out of the car to inspect it. No physical modifications, because when you kind of try and put it back together, it never fits properly. You'll break something. And so the goal is to get code execution on the device without actually taking it out of the car. Second point is I don't want to write memory corruption exploits. For this, again, it runs Linux, it has a browser on it, it has WebKit, there's bugs and vulnerabilities to exploit there. The goal was to find a simple and reliable exploit that you can execute on this thing without, that everybody could kind of replicate. If I'm writing a browser exploit, you have too many versions, it's a complicated thing to support, and it wouldn't work for most people. So those are two things. We want the simple exploit and not taking the machine out of the car. On the other hand, what is my goal? So besides getting code execution on the device, on the car, the goal was to kind of explore the system and have the ability to write a custom application for it that would be able to display something on the display and receive inputs from like touchscreen inputs and so on. A guiding kind of demo app that I had in mind was a GPS logger, where I could make my own application that would run on the console of the car at all times and just log GPS locations to a file, which I could later read and use for something else. I go on long road trips, so this is kind of fun. When I'm done with the road trip, I can see the exact route I took while I was driving, maybe off-road or whatever. So yeah, those are our constraints and end goals that kind of guide the whole project. And so we set out to figure out how we can get access to the device. What is the attack surface that I can explore and potentially abuse to get access to the running system somehow? Some of the obvious choices when dealing with these sorts of systems is firmware update mechanism. That's where the device is at its most vulnerable. At the point where firmware is being updated, all guards are down, and it's easy to mess up that process. So it's kind of a good starting point to try and find vulnerabilities in the firmware update process to easily get to implant your backdoor on a device and get access through that. Second thing is a Bluetooth stack. This machine has Bluetooth running on it at all times, so you can connect to it via your phone. Bluetooth is interesting because that would mean an attack would be potentially wireless. I wouldn't definitely need to take the machine out. And yeah, it's a good option to start exploring for. USB devices, so there's a USB port in the car that's connected to this head unit, so potentially I could plug something interesting into that USB port that would get me access to the machine. So all of these things I wanted to walk through and see if I can find any bugs that would kind of get me code execution. I took some time to go over the firmware update mechanism, and it turned out it's pretty solid. The firmware isn't encrypted, but it's properly signed. You can probably break it, but there wasn't an obvious way through it, and there were other complications, so I moved on to different attack surfaces. And we'll walk through what the eventual exploit was. I mentioned USB devices, and so there's a USB port on the head unit, and I wanted to see what kind of devices are supported by the head unit, by the infotainment system. Because, as I said, it runs Linux, and that USB port is meant to be used for a USB key, like a memory device, like a flash drive, for you to load music off of and stuff like that. But since it's a USB port, maybe it supports some additional stuff. And one way to figure out what drivers the device already has is to kind of iterate through all of the devices and look for responses. There's this tool called Phase Dancer, which is a USB debugging tool, low-level USB analysis tool. And as a kind of application that uses Phase Dancer, folks from NCC group made a tool called UMAP2, which uses Phase Dancer to do all sorts of interesting things. And here in green, you can see this is how you basically use the tool. You can tell it to brute force vendor and product IDs, listen for like what's happening on USB, and it will tell you if a particular vendor and product ID does actually have support on the device that you're targeting. So I run this on the head unit, and it comes back with one result. There are more results, but in this case, I narrowed it down to one, where it says that besides a flash memory stick, what else is supported on that USB port is an Ethernet adapter. So it says here, USB 200M 100 base TX adapter is a network device. So if I plug in a network device, like this one, into the USB port, suddenly the head unit, the infotainment system has Ethernet support. So you'd think, okay, it has network, I can connect to it and maybe talk to it over that. So I got Ethernet adapter connected to the network, but didn't get anything. It turns out no open ports on the device, nothing's actually running on it. So even though you can connect to it, you're on the same network with the device, you don't get much from the get-go. And that means at some point you have to start getting your hands dirty. This is one other point that I wanted to make in the presentation. When doing these sort of projects, you're always going to need a sacrificial device, one that you are willing to kind of break, destroy, or break, because while doing testing, things are going to break. So I got a sacrificial device from eBay, from a wrecked car or something. That is exact same model as the one I have in my car, so I can explore this one and do more invasive testing. The goal here is to use this device to figure out access to the device, and then use some sort of access to the device to figure out a non-invasive exploit that you could use on the one that's still in the car. Just to kind of show how it looks like, there's USB ports in the back of the device. It's connected to the car. There's an ignition signal that you need to enable to tell this thing to boot, which gets turned on by your key. There's a GPS antenna and so on. The device itself, when you take it apart, it reveals that it actually runs an ARM chip. The whole platform is manufactured by Bosch. So Bosch makes these head units for Nissan, also sells the same thing to GM and other car manufacturers, and they look slightly different, but they're all the same platform in the end. The device itself is actually, the platform itself was developed by NEC, and it's a very old thing, but in this picture, an interesting thing is these two wires that are coming off of it. Those are TX and RX lines for a serial console. So it was, with some tracing, it was relatively easy to spot that there's a serial console somewhere there, and I broke out these two lines so I'd be able to actually communicate with the device over serial. Which was all nice and dandy, but the console was locked. There's no, like, you can connect to it and see some messages, but nothing, you don't get like a shell access or something. A couple of things you can notice in this screenshot of a U-boot. This is a U-boot boot log, which is a standard bootloader. You can tell a couple of things that are of interest here. First is that it's booting a kernel image of some sort, and it says starting a guest OS. If you read closely through this, it means it runs two operating systems at the same time, which is a pretty unusual thing for an embedded device like this. So it's a dual-core ARM chip that runs two devices, two operating systems. One is Linux. The other operating system that it runs is an RTOS of some sort that we don't know much about. And you can see here also that it says hit any key to stop auto boot. So if you could interrupt U-boot at this point, it'll probably drop you into some sort of a shell where you could get command execution. So yeah, it's easy to get a root shell through U-boot because you can just break at it, change the boot environment, and tell it to boot into a shell, and get like a command prompt that you can type commands into. And then when the system boots, you can just enable SSH on it and use that to access the system over network with that Ethernet adapter from earlier. And this is where the real work begins, because now we have access to the device and we want to find that non-invasive exploit. So I don't want to take the device out of my car to solder those two wires on. I need some way to get the same shell on the device that's in the car without taking it apart. We go back to figuring out how the system works. We go back to figuring out the attack surface and trying to find some vulnerabilities to exploit. I quickly figured out a bunch of scripts that run every time something happens in the system, and I was looking at those that would be triggered by something that's external to the car. I quickly zeroed in on a very, very simple vulnerability in the way auto-mounting of file system works on this platform. So when you insert a USB key, this shell script gets run to mount that file system, and it has it properly escapes the commands, but there's a very subtle vulnerability here where the mount point, the destination mount point for the command is made up of the name of the device itself or the file system ID itself. So if you can do directory traversal and make it mount the file system that you supplied or whatever path on the device itself. So what we can do is mount a USB flash to an arbitrary address, so we can put our external file system over something like user bin and replace all the built-in commands with something that we made, which leads us to code execution in an easy way. So quote-unquote jailbreak exploit for this sort of device is super simple. You make a USB file system that exploits this vulnerability that just runs a command that enables SSH and drops the firewall and reboots the machine. So the whole procedure for actually exploiting this in the car is you take the USB key, plug it into the USB port, turn the car on, it boots up, it mounts the file system, that puts a backdoor on the original file system, enables SSH, you reboot the car or turn it off, turn it on again, and now you have a SSH shell running on the thing, and you can just connect to it over the network using that Ethernet adapter from earlier. So super easy and exactly as we wanted it. Not invasive, doesn't require any messy exploitation or whatever. It's just a simple command injection basically. And that works. When you kind of execute it on the system, I can get a shell and I can see that I'm root on the car, which is kind of entertaining. From this point, there's a lot of work ahead, a lot of reverse engineering, because, okay, we have access to the system, I got a root shell, but I need to make it do something interesting, and to be able to make it do something interesting, we want to figure out how the system actually works. So we want to reverse engineer the IPC mechanism, we want to reverse engineer that RTOS, real-time operating system. So the reason for the split, why is there like Linux and an RTOS, is RTOS is the thing that talks to the car, and Linux is the thing that shows you, that plays music, shows you pictures or whatever, runs the UI. The reason for that is if Linux crashes, you don't want your whole car to crash, so RTOS is always running even if Linux crashes. So there's two operating systems, and if we want to get interesting data from the car itself, or send some interesting data to the car, to Canvas or whatever, we'd have to go through the RTOS. So there's a lot of reverse engineering involved in that. I'm not going to go through too many steps about this project. There's an extensive project log with all the technical documentation on my GitHub repository that goes deep into the system overview, the RTOS interactions, how the RTOS works, how the custom applications work on this platform, the very important IPC mechanism, which we can use for writing extensions for this, how you can make your own C and C++ applications, Python code, and so on. I published the project and asked everybody who tried it to kind of report back the versions and the types of cars that this worked on. So many people wrote back to say that they tried it on their cars and had fun with it. So we have a bunch of different firmware and hardware versions and a bunch of different cars from Nissan. The latest one was from 2018. I guess in 2019 they switched to a different Android-based platform, but there's a high chance this sort of work will be useful for those platforms as well. And in the end, I did achieve the result that I wanted. I did write a demo app that does log GPS to a file that lets me make kind of animations afterwards of the route I took when I was driving around, or that's the car head unit project. Again, from the start, the goal was to get a non-invasive exploit that would get us a shell in the system that would let us modify the system and make it do something interesting, as opposed to the one that's locked down. That brings me to the second project that's not really connected to this one, but it embodies the same ideas. I want to talk about this weird-looking camera. This is called Lytro, and this is a camera from the future. This was the camera from the future in the year 2012. It's not a regular camera, it's a light field camera. I don't know does anybody remember these being like advertised, or has anybody seen them? They're kind of rare because this was a commercial flop. Google bought the company, tried to market it, tried to sell it, but it was too expensive. It didn't solve a problem that it tried to solve, and kind of nobody wanted it. The idea with this is it's what the hell is Lytro, and why is it a special camera? It's a light field camera. It doesn't record pixels, it records light rays, which is kind of weird to, it's a relatively simple idea when it comes down to it, but when recording that light field, instead of just pixels, you can computationally interpret that data and generate a different image. The result of which is that you can take a photo, record that light field, and you can change focus in the post. So you can take a photo and then decide where the focus of the photo is. You do get a little bit of 3D-ness to it as well. But so yeah, it's a weird 2.5D camera, plus that killer feature that it had was that ability to change focus in post. In 2012, we already had good cameras that you didn't really have to struggle to focus, so the project was doomed from the start. But it had a very, very interesting tech. As I said, it solves a problem that nobody had, was a commercial flop, but it's a very cool product because it had a built-in battery, it had Wi-Fi, it had built-in storage, the very cool lens that's a f2 200mm lens, which is pretty nice, but the camera itself is relatively unusable. It did have this weird design where it's kind of like a cigarette box or whatever. It won't fit in your pocket, so no wonder nobody kind of took photos with it. So yeah, long story short, the camera was a commercial flop. No one wanted them. There's plenty of them on eBay popping up here and there for pennies. They're relatively cheap, and I thought it was an interesting relic of a failed product, so I wanted to get one just to have it for fun. But then realized, like, why don't I dig into it? If I could get code execution, maybe I could get something interesting out of it. Also, kind of fun to look into how things work. So again, with this project, constraints and end goals, again, we want no physical modifications if possible. So I want to get code execution on the device somehow without actually damaging the device. And as far as goals go, I wanted to unlock, to figure out if I could make some additional features which would make it a lot more usable. Like if I could make it into a webcam where I could stream live view from the camera, that might make it into a useful thing. Like a motivating example here would be to monitor backyard squirrels. So I would have a camera set up in the backyard with motion detection. Squirrel runs by and the camera takes a photo. It doesn't know where the squirrel is, so you can focus on the squirrel after taking the photo. It's kind of joking. It doesn't have a purpose, but that's kind of the guiding goal for the project. So after disassembling the device to figure out how it works, how it's built up, you can very easily spot serial access on the device, but it's relatively useless because the bootloader is locked. There's nothing nothing running on it. So even though you have serial easily accessible, you don't get much. We can start with, again, mentioning you'll need a sacrificial unit to do the testing on. This one has wires running out of it because it connected a bunch of wires to that serial port so I can examine it. And yeah, having a nice test environment is crucial to be able to test things and test hypotheses while trying to break into the device and while reverse engineering it. So as I said, the bootloader, even though we have access to serial, the bootloader is locked, so we don't get much out of it. It just spits out this small message at the beginning, and then it's silent. It doesn't take any keyboard input or whatever. So we'll have to dig into the firmware to figure out how it works. Getting the firmware is easy. People made archives of them. You can also dump it from the device. And when you kind of try and disassemble the firmware, it's built up of a bunch of ELF files, which is weird. Seeing ELF files will lead you to believe you're dealing with the Linux platform, but in this case, it's not Linux. It's an embedded device. It's a microcontroller of some sort. So why ELF files is a bit confusing. Turns out after a little bit of reversing that the ELF file format is used to kind of have a nice way to make a memory map or map binaries into memory on the system. So all of these ELF files are actual binaries that contain code, contain libraries, but they're statically mapped to a certain address in memory, which is what they use the ELF standard for, or format for. And yeah, I was running ahead of myself there. The device is running an unknown RTOS. The chip that does all the work is made by this company called Zoran. They make camera on a chip products. Basically, a bunch of dash cams use the same platform and use the same type of software as well. So while reversing this, I figured out they can get the same thing to work on a dash cam. So we get the binaries, and then we can fire up Ghidra or your disassembler of choice and start digging into the code to figure out how to get access to this device. Once you kind of open these binaries, it's relatively easy to figure out which binary does what. Some implement libraries, some implement actual applications that run on the device. Like this is an example from the bootloader code, and we can see, okay, it outputs those messages, but it's locked in some way, and there's nothing interesting we can get from it. So since the serial console was locked, the bootloader was locked, we can skip playing with that and dig into USB implementation and Wi-Fi protocol, because that's the other part that might be a possible attack surface to get access to the device. And it has like a documented USB and Wi-Fi protocol to control the device via phone. There used to be an app to control these, so you would push a button in an app and it would take a photo. And the communication protocol that goes over Bluetooth is relatively simple. There's these command classes that you send command types with expected payloads and receive data back. So I started digging into the firmware, trying to find where these things are implemented in the code. And after spending a while kind of piecing together how the system works, what the functions are, what the functionalities are, reversing things here and there, making a lot of structures and defining a bunch of function names, I ended up at this function, which is obviously some sort of a command interpreter. You have a large switch statement that compares bytes for commands and then executes a different command handler, which is what I really wanted to find, because this is where my data gets parsed, and this is where a potential vulnerability might be. So again, long story short, went through all of this code in the disassembler, figured out all the commands that are implemented, and there were a bunch more than were available from the app. So there were hidden commands, undocumented ones, and yep, this is an example list of them. There's a couple of interesting looking ones, like inject UART sounds interesting. That might be an interesting feature to abuse. There's also exec command, which might lead to some interesting way to access the device and so on. So I kind of documented all of these individual commands by reverse engineering the command interpreter and figure out which one of these might be interesting to look deeper into. Like obviously we're trying to get code execution, it already has a command that's exec command. So yeah, I want to look at that and figure out how that works. It turns out the exec command doesn't do code execution, but it does something weird. And while kind of reversing it, I figured, I saw it's using SHA-1 in some way. And when I saw it's SHA doing something weird with hashing, it's a command that's doing something interesting, I figured, okay, I'm on the right track here. So I want to dig deeper into that exec command to figure out what it's doing. And those SHA calls, when you kind of figure out the locations and everything, turns out it's taking whatever you sent over over the wire, appends please to it, hashes it, and then compares it to a secret built-in hash. So this is basically a backdoor into it's a hidden command that expects you to know a secret value to send to the device, and then it unlocks the device. When you figure out what you need to send the serial number of the device with please attached. So when that hashes, it will pass this check and the device will be unlocked. And sure enough, when you implement that in the code, send it over, you get the unlocked device. Suddenly the serial console starts working. Suddenly you have open ports on the device and you can connect to it and do a bunch of other stuff. So by figuring out that command, you unlock the device and you can play with it. We get code execution on it. After that unlock, a whole slew of extra commands become available. You can, through this code execution, you can easily enable manual controls like controlling the ND filter, the zoom level of the lens. You can enable live view, so you can get the video data out of the camera directly. And yeah, there's a built-in command shell basically with all of these very nice implemented commands to be able to debug the system and have a bunch of fun with it, I guess, to further kind of ease reverse engineering and doing something interesting with the device. So we can unlock the camera over Wi-Fi or USB by sending that correct hash, the secret message that it expects. We don't need to disassemble the device. We don't need to solder anything. It's just, I can just have a device with Wi-Fi on it, send that unlock code, and suddenly the device is much more usable. So I implemented a remote shell over Wi-Fi basically. When you turn on the device, it listens it makes an access point and listens on a port where it has a shell enabled, so you can control the device over that. Here's a small demo. I implemented a Python library that lets you control the camera in a lot of details. So here's how the code looks like really quickly. This will just wiggle the lens a little bit, zoom in and zoom out, and then take a photo and get you that photo on the computer. Some other features are like the live view works over UDP broadcast. So when you enable live view, it just starts sending MJPEG frames over the network, so you can stream those and view them in a video player, basically. So yeah, you can capture them with FFmpeg like this. And with this, I consider the project done. I get access to the device. I can build my own code for it. I can I can make additional scripts to utilize the camera and so on, and have some more fun with the camera. Otherwise, it was a useless piece of junk. That kind of concludes my project that I wanted to present here. These are like hobby projects I spent some time on, and I wanted to kind of point out some of the takeaways that I wanted to give in this talk. These projects, when I'm kind of choosing a device to kind of take a closer look at or have fun with, I'm focusing on some sort of an interesting device, something that has a weird set of features, like the car head unit obviously fits in the car that I already have, so it's kind of interesting from that point. The camera is interesting because it's a weird camera that has that light field technology on it. I have a photo here of a thermal camera. That would be something that would be interesting to reverse engineer and get access to, because those are not super common. So you'll always want to get a spare to experiment on, and want to make yourself a nice test environment to be able to reproduce stuff and easily test ideas. I find it very important to outline those constraints and end goals from the get-go. There's that meme of everybody getting Doom to run on weird hardware. Running Doom on the device can be a valid end goal, but you can also come up with something kind of utilitarian, in a sense, a goal to achieve some sort of to add some interesting functionality to the device. Second thing that I wanted to point out, that tools are relatively cheap for doing this sort of work. There's an abundance of material out there for how to get started with this. There's YouTube videos, wiki pages, write-ups, articles, you name it. It's easy to kind of get access to the way to learn this sort of stuff. Like some of the tools, like PyPico is a super useful debugging thing. Ghidra is free, which is good. The biggest boon to reverse engineering, having access to such a great disassembler with the built-in decompiler is awesome for hobby projects. So yeah, you can easily start with this sort of work, is what I wanted to say. It is of utmost importance to document everything, no matter how uninteresting it might sound to you. Put it on the internet, document it, because several years afterwards, someone might be at the same point trying to do the same thing, and they will thank you a lot if you already documented it very well. I use GitHub as a wiki, basically, for these sorts of projects, because it's easy to pull stuff from other people, have an issue tracker and a comment section there, which helps with disseminating this information and working with other people on this sort of projects. But yeah, definitely, if you're doing this sort of work, publish it in any shape or form, and let people know, like tweet about it, or toot about it, or whatever is the current acceptable social media information spreading thing. But yeah, make sure people hear about it, I guess. Even kind of the projects are trivial, but it's good to let people know. And that brings me to the end. You can find both of these projects, the detailed write-ups about these projects, on these two URLs, or you can scan the QR codes. You can reach out to me. I'll be around at the conference to ask me some questions. I think we're at time. But yeah, thank you everybody for listening to me rambling, and hope you enjoyed it.
Are there any questions?
Thanks, really interesting. Did you also look at other head units, since you mentioned that this is a somewhat standardized Bosch unit? Did people also try it already on other cars with the same kind of connections?
So I did mention that like GM uses a similar platform. So these things are pieced together from so many manufacturers that it's not the exact same, platform, but pieces of it are very similar. You can find very similar pieces of the whole firmware in other devices. So yeah, some people reached out that they were working on some GM Chrysler units, I think, that use the same RTOS and the same library to communicate between the components, but weren't like that simple exploit that I made didn't work on there because that part of the system is different. But the reverse engineering that I put in and documented, they were able to reuse and use it on their platform. So it's not. There are some that would be directly exactly the same, and it would work on other cars, but
I'm wondering about like if Stellantis would use all the same kind of head units, same software, standardized at that level too from Bosch. That's, okay.
Any more questions?
How did you manage to pull the firmware of the Lightro? Like, how did you manage to dump it through Word or?
So the Lightro itself, I think I have it in the documentation. The firmware itself is on a flash that's on the device, so it's relatively easy to kind of. It's a non-flash, so there's standard ways to interface with it, and like with SD cards and stuff, but, to read it up. But,
thank you.
Hello. So did you have a lot of failed projects before you find out the successful ones?
I mean, not exactly. As I said from the beginning, these are relatively low-hanging fruits when it comes to secure devices. These aren't secure at all. And with these sort of projects, it's kind of you always find something. So in more professional work, I did have failures, obviously, where things don't go the way you want them. But not in this case. I don't think I would have an example of a hobby project that kind of. I do publish everything, even if it wasn't successful. So yeah.
And one more question: how did you find out that the Bosch head unit had Linux? What was the hint?
So you can actually just download firmware updates online for it. And besides that, like since it runs Linux, it has to have a GPL license somewhere on the thing. So when you're scrolling through the menus, at some point you'll see references to Linux kernel and licensing and stuff. So that was easy to kind of guess. But yeah.
Thank you.
Any more questions?
So with the head unit, did you ever try going through CAN at all? I noticed nothing was hooked up there.
Yes. As I mentioned, there's a communication layer that goes like through the kernel, talking from Linux to the RTOS side of things. RTOS is the one that's connected to the CAN bus, and it receives messages. And this particular car, there's several CAN networks on it. So the infotainment system is only connected to like informational one. You're not on the same CAN network as the ECU is or something. So there wouldn't be a direct path to controlling something about the car from the head unit. You could control like AC maybe, some stuff that's on that kind of low priority CAN bus, but not the more important stuff, I think. It was more isolated. And I could, in my documentation, there's a couple of scripts that do let you sniff CAN bus messages through this, but only specific ones because they get filtered by the RTOS, and it's a bit. Yeah, the head unit isn't that tied to the car system itself, so you don't get full CAN bus access from it. Is what I'm trying to say.
Yeah, so the access you do have, were you able to poke at like the diagnostics? and like trying to read memory out of by diagnostics?
No, not exactly. You don't have that level of low-level access to a CAN bus exactly, because it's it's slightly more complicated. I guess in this case, it's like you already can connect to the OBD port more directly than through this unit, but it's a bit, yeah.
Any more questions?
I can elaborate more about it, and yeah.
So thank you, Alex. Everyone, please applause.
Thank you.